I hope you can hear me. As already said, I'm Rob. I'm a staff research scientist at Sakana AI. And first off, I want to thank all the organizers, including Richard, Dan, and so on. Thank you for putting this together. I think this is a great event to bring sort of the automated discovery community together. Yeah, so today I'm going to talk about ShinkaEvolve and automated discovery more generally, and I will put a focus on basically everything that happened since the first release last September. And this is joint work with Yuki Imayuku and Eduardo Sitting. Whoops. So basically, when I give these talks, I like to start out with discussing sort of one of my favorite booklets. And this is a book by Austin Kleon, where he essentially looks at creativity in humans and how to essentially find your own style. And so in this booklet, he makes this example of Pablo Picasso being sort of oftentimes in the public perception a genius who essentially sort of took a shower, woke up, and sort of had this idea for cubism. But in the book, he basically discusses that Picasso was much more a child of his time, right? So during his period, there were many different surrealists, including Joan Gris, Miro, Dali, Cézanne, and so on. And basically, he found his style by copying and imitating pieces from their work, right? And this is basically how Cubism came about. So, more specifically, Picasso himself once said, "Good artists copy, great artists steal." And so, what's important with this statement is that he didn't mean this sort of in the literal plagiarism sense, but he meant it more in the sense of basically finding your own style by creating a mosaic of sort of inspirations. And so nowadays, sort of this is really important because we have to ask ourselves whether or not language models or language models with tools, aka agents, are basically, yeah, good artists themselves in the context of automated discovery. So now, before I essentially go into the details of the talk, I quickly want to say that a lot of what we're doing nowadays has already been around for a while, right? So the previous speaker on LLM for AD basically already mentioned that automated discovery is something we've been doing for, yeah, quite some time, right? So I myself, during my PhD, worked on sort of using numerical black box optimization and evolutionary optimization together with hardware acceleration, GPUs, TPUs to do automated algorithm discovery for evolutionary algorithms themselves. But we've also been working on a bunch of settings where you apply this, for example, to the discovery of reinforcement learning components and so on. And then in 2024, I sort of had the privilege of working with a good friend of mine, Chris Liu, on this paper called Disco Pop, where we basically saw that instead of doing numerical black box optimization, you could use much more powerful mutation operators, namely language models, right? So basically there we showed that you can use LLMs in a closed loop to propose post-training objectives for LLMs. And by doing so in a closed loop with the verified information, you could basically discover novel objective functions. And this was very much akin to what I showed you before, where we could see sort of interpolation between different concepts from adjacent fields and so on. And then we continued this line of work in the form of the AI Scientist, which was recently published in Nature. But today I kind of want to talk about something else, namely ShinkaEvolve, which is closely related, but essentially tries to see how far one can scale this in a sample efficient way. So as already discussed in many previous talks, approximately one entire year ago, AlphaEvolve came out as sort of a child of both AlphaCode and FunSearch. And when I saw this, I was really, really excited because it sort of proved for, let's say, one of the first times on a large scale that one could make discoveries across mathematics, computer science, and so on, that could actually sort of feed back into the loop, right? So one of the most exciting results from AlphaEvolve to me was essentially this discovery of a self-attention kernel written in Palas, like this JAX language that could then be fed back into Gemini pre-training, right? But one or two things that didn't really sit right with me was that EvoLLM is closed source. By now, you can use sort of a Google Cloud product, but it's still sort of hidden away, and that it still was very, very sample efficient. So this sort of prompted me to work on ShinkaEvolve, which tries to overcome both of these problems by being open source and Apache license, as well as focusing very strongly on sample efficiency and cost efficiency, right? And so in this plot here, before Henrik already spoke about circle packing, basically what we showed here was that we, with ShinkaEvolve, could basically beat both LLM for AD, AlphaEvolve, and OpenEvolve in terms of discovering a state-of-the-art circle packing solution with less than 150 program evaluations. So what did we basically do? Wait a second, let me see if this, okay. Here you should see an animation, but instead you see a static image. But what's important about this plot is, I think, something that lies at the core of all these evolutionary discovery engines, namely in the right plot, you can see that essentially the line to the best performing solution that ShinkaEvolve found is not just essentially a cumulative max, like a step function basically, but you can see dips in the performance, right? So what I'm plotting here is the path to the best solution in the end, or to the program that led to the best solution. And what you can see here is that in order to discover basically the best solution, you need to use stepping stones of programs that essentially were evaluated before. Okay, so what did we do in order to improve the sample efficiency of sort of these evolutionary code search methods? There are basically three sort of ingredients that go into this special sauce. One of them is the way how we sample candidate programs to act as parents for mutations. So what you can see here is basically we're showing a sampling distribution, and in the sampling distribution, we're essentially trading off the performance of a previous program with the number of children it has already generated, right? So as you can see, basically programs with high performance are sampled more often as parents. But if they have already given you a lot of children, which, for example, didn't improve, we're down weighting this probability again, right? So we're trading off exploration and exploitation in terms of what programs act as inspirations for the next generation. Down here, you can see an ablation where this clearly sort of beats just randomly sampling from the LLM over and over, as well as sort of hill climbing. Another thing we did was instead of sort of having to rely on Gemini models, because this is on brand Google, right? We could use, basically all providers accessible. And the question then becomes is, okay, how do you query these LLMs, right? So you can either give fixed weights to them, like it's done in OpenEvolve, for example, or you try to do something that smartly sort of schedules which LLM to ask, right? So we implemented a bandit algorithm that looks at how well does an LLM in generating an offspring that then improves the performance of its parent, right? And LLMs that are sort of consistently improving upon parent solutions, they get sampled more frequently than the ones that don't. And again, we have an ablation. You can see if you just sort of use a single LLM or you just use a uniform ensemble, these two are outperformed by doing sort of this adaptive sampling from the mutation engine. And finally, in order to improve sample efficiency more, we also leveraged a rejection sampling approach, right? So basically, you sample from an LLM, and then the question is, do you spend time evaluating it, or can you do better by basically resampling a new LLM? And in order to implement this, we basically did two things. We first take the raw program, we text embed it, and then we essentially score it based on cosine similarity against all the other programs in the archive of programs you've previously evaluated. And if it essentially crosses a threshold and is not novel by cosine similarity, we additionally ask an LLM to compare the closest sort of program with the sample program, and then make a decision whether or not we should actually evaluate it or resample. Good. So one thing, here we go. that's kind of important about all of these methods is, I think, the usability. So there are many different people from sort of adjacent fields or from fields that have nothing to do with machine learning. And in order to make it easier for them to actually work with this in their domain, we set up this web UI where you can basically look at many different important parts of the sort of ShinkaEvolve development pipeline. You can look at scores, you can look at cumulative costs, you can look at the search tree, you can basically inspect evaluation logs, you can look at the code, etc., etc. And I think something that's kind of important about this is that it allows you to essentially also use this tool as a co-scientist, right? So oftentimes you start with a program and you have a verifier that you've kind of manually written or asked Claude Code to write it. And there might be some reward hack loops and so on. And then you run Shinka once and you kind of identify these hacks and then you fix the verifier, right? And having a quick way to access this is pretty important to essentially making progress. Okay, next up, there are many different results in the paper. Like we applied this to discovering mixture of experts, loss functions for pre-training. We apply this to competitive programming. We apply this to agentic harness design and so on. But like one of my favorite results that came out of this after we published the paper was one of my colleagues, Takuya Akiba, who's like a, let's say, legendary Kaggle Grandmaster. He's been doing sort of competitive programming competitions all his life. And he, together with Timunagi, sort of competed in this ICFP programming contest, which is like a functional programming contest that is kind of unique in the sense that you can use whatever tool you want. And basically, the task they were given was an SAT solver problem. And they basically used ShinkaEvolve to optimize variable encodings for the downstream SAT solver in order to essentially speed up as well as provide higher accuracy of the solutions. And this led to them actually winning the contests, right? So coming back to what I said about the visualization setup, I do think these tools are now more and more essentially, co-scientists, and we still require some human intervention in terms of, okay, how do we set up the task? How do we make sure that reward hacks don't occur? Yeah. So one more thing, like in ShinkaEvolve, we also used essentially a heuristic programming benchmark developed by Yuki from our team called ALE Bench. And Yuki had implemented a beam search agent. And what we did is we basically used the solution that was discovered by this beam search agent, and then we used Shinka to refine it. And we could essentially find improvements that then on one of the tasks essentially led to improving the performance from being fifth to second in like a competition, offline after running this. And since then, like Yuki has continued working on this, not with Shinka in the loop, but basically a different harness. And he managed to actually find also in a real world contest with real time constraints, a solution that could win the entire contest. Okay. So now let me quickly talk about what happened with Shinka since we released it. So there were many sort of practical improvements that we did. So basically one of them is we spent a lot of time on improving the throughput of Shinka so that it can scale with more hardware resources. And I do think something that's sort of important to keep in mind is that there are basically two settings. So one setting is the one where essentially your evaluation is faster than the way how you sample the program proposals. So this is, for example, the case for all the math tasks like circle packing, right? So most of the times you're bottlenecked in terms of LLM query generation and not in terms of the evaluation. And the other scenario is basically the one where this turns around. Sampling is basically fast, but evaluation is cheap. And basically, depending on how how your specific problem is set up in terms of verification, you need to take different precautions. And with Shinka, we're essentially trying to make the whole pipeline as linearly scalable as possible. And you can see essentially here in this plot below that with more resources, like more CPU resources, for example, we get almost linear speedups in terms of the time for running an entire Shinker experiment. Um, Related to this, one question everyone can ask themselves is if an expensive model costs 10x the amount that a cheap model would cost in generating a proposal, sometimes it might just be better to ask the cheap model 10 times than to ask the expensive model a single time, right? And so one thing we wanted to achieve is basically make the system more cost aware. And so in order to do this, we essentially extended um, this banded ensembling strategy for selecting which LLM has to act as a um, candidate proposal LLM by essentially calculating running means of API costs while you're running Shinka, and then downweighting or making essentially the sampling process more or less cost aware. And so this is like already by now, given that 3.5 Flash is already out, like a bit of an outdated result, but the key takeaway is still the same. So what you can see here is we have GPT, not GPT, Gemini 2.5, 2.5 Pro, Flash and Flash Lite. So Pro is the most expensive, Flash Lite is the cheapest. And we have this cost awareness coefficient, and 1 is essentially high cost awareness, 0 is low. And if you're not cost aware, Gemini 2.5 Pro will be selected the most frequently, simply because it's more powerful, essentially. While if you make it very cost aware, essentially you can use, or the selection will opt to choose Flash Lite more frequently. And when you essentially look at the cumulative costs of this experiment, you can see it's much higher if you just use Gemini 2.5 Pro. Okay, so throughput and cost awareness were two of the major improvements we worked on. But we're now in 2026, right? And now essentially at the point where we're all trying to reap the benefits of agents. So let me quickly take a minute to discuss sort of, let's say, competitors, even though I don't view it like that. So since AlphaEvolve, as already covered by others, there has been a lot of work on different evolutionary agentic systems, and they kind of take all like different angles and perspective onto this. And I do think they are all fruitful, right? So, for example, learning to discover at test time, fine tunes on traces during the evolutionary search on open source models like GPT-OSS. Sky Discover and EvoX, they allow for sort of explicit human steering of search processes. OpenEvolve is sort of the OG in the game, I would say. And now with auto research, as well as sort of Claude Evolve and so on, we have systems that are actually using sort of agents as mutation operators. And so what we also did since the initial release is we essentially provided two agentic integrations. So one of them is basically a set of skills that you can use in Cloud Code, Codex, Pi, Gemini CLI, and so on. And this basically informs the coding agent about the grammar, syntax, and interface to ShinkaEvolve. So you can basically just ask a coding agent to set up a task you're interested in natural language, and then it will do this. And you can then also instruct it to run the search and basically guide through the search process via Cloud Code. The other thing we worked on is basically moving away from just supporting APIs and you having to pay all the time. You can now also use basically your codecs and your Cloud Code subscriptions to generate mutations in a safe way in like read-only mode, basically. So the harness still does essentially the processing of the mutations and the evaluation, but you can use this headless CLI I worked on to basically generate mutations, so you don't have to pay on the top. Like two more things really quickly. I do think in general, like benchmarking these agentic evolution harnesses is very hard. I think Henrik already spoke a little bit about this. Oftentimes it's not super trivial to disentangle how much information from the verification and building sort of this search tree is actually relevant for finding a good solution, and how much of this information is already in the LLM, right? So this was work done by an internet, Sakana, where he basically showed that for many of the math tasks, a lot of the information is already in the trained LLM, and you can just sample extremely widely without doing all of this search, and you can beat both Shinka as well as AlphaEvolve fairly regularly. Another sort of core challenge with all of this is that oftentimes when you apply mutations repeatedly, you see something I call code swelling from like the genetic programming literature. And this basically means these programs become longer and longer, and they tend to overfit the problem in a certain sense. And it makes it harder to actually do real open-ended exploration because you're sort of zooming into local optima instead of exploring diverse ones. Good. Just to wrap up, like all the code, as I said, is open source, Apache 2 available. Here's just like a snapshot of how to set up a task. I think we're sort of very quickly progressing into a world where we're no longer vibe coding, but we're sort of doing vibe discovery. I hope that the agentic integrations that Shinka now supports are sort of valuable and fruitful for this endeavor. And yeah, with that, just want to quickly put on my Sakana employee hat. We've last week started a new lab called RSI Lab, which builds on top of all the automated discovery work we've done in the last years, including the AI scientist, the Avon Gödel machine, ALE agents, ShinkaEvolve, and so on. And yeah, we're recruiting. And if you're interested, then please feel free to Google my name, find my email address, and reach out. And with that, I'm happy to take questions. Thank you so much.
Thank you so much, Robert, for the very interesting talk. Perhaps we can go through quickly to some of the questions here. So there's a question from Enrique. Regarding the rejection sampling, how do you handle child solutions that are parameter tunings of their parents? For example, the child is simply changing some parameters of some algorithm used by the parent. How do you
Yeah.
prevent this from being rejected?
Yeah, that's a good question. So I also thought about this when setting this up first. Like if you, for example, tune like a neural network training script, and the only change is changing like a learning rate, right? Then the
Mhm.
code embedding distance will be minimal, right? So you're going to reject something even though like it might be like what you're actually trying to do. So this is essentially where this LLM novelty judge comes into place, right? So it takes the two closest programs, right? And it checks whether or not the change should still be accepted, yes or no, right? Yeah.
Okay, so maybe just quickly a related question here. So how do you set the threshold of rejection? Does it depend on the task?
Yeah, so I do think this is a valid critique. So we found that like 0.995 is good, right? But
Mhm.
in general, like all of these systems, they come with a lot of hyperparameters. And I do think a really great contribution to the field would be something like the atom of code evolution, right? So finding something that's very robust. Yeah. But there are ablations in the paper, and there is like yeah, let's say a confidence interval of values one can try. Yeah.
Okay, that makes sense. Yeah. So maybe we have time for one last question here. So despite using the quality diversity mechanism and also the novelty rejection mechanism to prevent mode collapse, do you still observe the archive converging? And if so, what are some filler nodes you see even with this diversity mechanism in place?
Yeah, I think this is probably also going to be part of the panel later on.
Mm.
Uh, yeah, I mean, I think no one can claim at this point that they have fully
Mm.
unlocked true open-endedness, right?
Yeah,
So
yeah.
there is convergence, right? I do think sort of what I alluded to in the end, like this code swelling phenomenon, namely that essentially the files get too large to essentially make meaningful, let's say,
Mhm.
ablations or changes to the script is one part of this, right? So yeah, I do think there are many ideas what one can do,
Mhm.
but I wouldn't claim that we have yet in the field generally seen like true open-endedness in the sense that it would more accelerate than stagnate. Yeah, but it might also be just a function of the problems we're dealing with. Yeah.
Right, of course. So there's still a lot of open problems that we can discuss. So maybe later stay tuned to our panel discussion where Robert is also part of the panel. So If you still have more questions, we can keep the conversation going on in the chat. Otherwise, let's thank Robert for the great talk.
I'm
And
also in the breakout session if anyone wants to, yeah, ask directly.
yep, yep. Thanks for the reminder. And actually, that's our